Hello, everybody. Okay, so as you can see, we have a new class. They are practicing social distancing, so you have nothing to worry about. Today, we are going to be taking a totally different perspective in statistics. We're going to be looking at probability. So probability is the study of chance. So statistics takes something that happened in the past. Statistics looks at the past and probability looks at the future. We've been talking about a lot over this past semester, the fact that one of the things that statistics does for us is it helps us make decisions. So for statistics, we're making decisions based on what's already happened. How many people have survived a certain surgery? How many car accidents have there been? What do we have to do in terms of hospitals for preparing for the coronavirus? I also want to mention coronavirus. There are a tremendous number of statistics out there. If you want to know more about them, then please just let me know. I haven't been talking about them, even though it seems so apropos at this time, because I just feel that you need a break from them. I'm sure a lot of you are reading about it and watching it. But if it is something that you want to understand better, then absolutely just put a note up on Blackboard. Okay, but all of these statistics, all of these things that we're doing in terms of decision making, it's based on things that have already happened. Whereas probability says, okay, well, what could happen? And we make decisions based on that. So there are two different types of probability, and we're going to touch on both of them today. The first one is classical probability. That's what we're going to start with. And for classical probability, we're really looking at possible outcomes. For different events, and again, we'll define events a little bit more clearly in a few minutes. The other type of probability, which we'll talk about second, again, this video is really just an intro to each, and then we're going to go into more depth over the next few videos. Empirical probability, that's the second one. Kind of a nice word. Really, it is. I like saying it. Empirical probability is based on experiment. So and we'll make this difference very clear, but quickly, just so that you're not going in blind. Think about classical probability as we're tossing a coin, the probability of getting heads is 1/2, because we could either get a heads or tails. Empirical probability would say, okay, well, instead of just saying it's 1/2, let's actually experiment and toss a coin 300 times. And if we get a heads 200 out of 300 times, then we're going to say the probability of getting another heads is 2 out of 3. In other words, if that was a lot to listen to in less than a minute, all we're doing is we're saying we're going to look at the number of heads that we got when we tossed the coin 300 times, and that's what's going to tell us what the probability of getting a heads on the next toss is. Whereas for classical probability, we're saying, well, either we could get a heads or tails, so it would be 1/2. Okay, so let's start with classical probability. Okay, I'm gonna So I'll write that down here so that you know that this is where we're starting. Okay, and a lot of this that I define here would be the same for empirical probability. So an event is an action. Think of it as tossing a coin. We are doing something. Picking out an outfit. We are doing something. This is an event. Spinning a spinner. We are doing something. Rolling a die. We're doing something. So if you're not doing something, if there's no action, we wouldn't call it an event. So sometimes people get confused about an event versus an outcome. The outcome is the result of the event. And we say possible because one event can have multiple outcomes. And if we want to talk about all of those outcomes, okay, then what we're saying is that we have a sample space. So a sample space includes all possible outcomes. Okay, as an example, you're going to see us using these types of examples frequently in probability. So the first example would be tossing a coin. So we'll say we're going to define an event, an outcome, and the sample space. So the event would be tossing the coin. Think of these as verbs, okay? Nice little reference to your English classes. This is a verb. It is an action. So tossing a coin is an action. One possible outcome is getting a heads. But the sample space would be all possible outcomes. So the sample space here would be heads, comma, tails. And notice what we did here. These are braces. If you look on your keyboards, this is what's typically up above the bracket on the keyboard. This is how we define a sample space. So we put all of the possible outcomes inside these braces. There is no special order to this. So we could say heads, tails, or we could say tails, heads, and they're separated by comma, okay? Another example. So in this case, we'll say that your event is rolling a die. So some people have gotten confused about this in the past, so don't feel bad if you're confused here. A die is one, usually when we roll something, we roll dice. When you're playing like a board game, you're rolling 2 dice. A die is just one of those. Okay, so you're rolling a die. Die is 6-sided. One possible outcome would be 1. And your sample space would be 1, 2, 3, 4, 5, or 6. Any one of those could be a possible outcome. Okay. If we say that you are choosing something from, if we say that you're playing a different board game, like Twister, let's say, and you spin the spinner, then spinning the spinner is your event. Your outcome would be a color, so it might be blue, and your sample space would be all the colors on the spinner. So it might be blue, red, green, yellow. I'm not sure what other colors are on the spinner, but hopefully you get the idea. It's any one of the colors. Okay, so in classical probability, the way that we define probability, we use the same symbols, they just mean different things. So the probability of an event is the number of desired outcomes over the total outcomes. When we say total outcomes, we mean the number of outcomes in the sample space. Okay, the number of outcomes in the sample space is always going to be greater than the number of desired outcomes, unless you're saying what's the probability of getting a heads or tails when I toss a coin. Okay, so the range is 0 to 1. Okay, probability of 0. This would mean the outcome is impossible. So, for example, that would be rolling a 7. Or I'll write it as 8 so that you don't get confused when you see it. 7. So rolling an 8 on a die. There is no 8 on a die, so it would not be possible to get an 8. That would be a probability of 0. A probability of 1 would be an outcome or an event that will definitely happen. So in this case, it would be rolling a 1, 2, 3, 4, 5, or 6 on a 6-sided die. I'm specifying 6-sided because there are some dies that have more than 6 sides. So up here I'll add 6-sided. Okay, there are dice with 8 sides. So you would definitely get a 1, 2, 3, 4, 5, or 6 if we roll a 6-sided die. So that would be an event that would definitely happen. There are some events that don't have a probability. Those events are things that happened in the past. So events that happened in the past have no probability. We don't measure it. So we wouldn't say it's a probability of 0. We're saying that there is no probability. So for example, if you're watching a basketball game on video, so if the basketball game already took place, the probability of the Knicks winning that game does not exist. Probability predicts the future. So if the Knicks already won or if they didn't win, it doesn't matter. The probability doesn't exist because it already happened. The probability of your having come to class on March 12th, I think that was a Thursday, on March 12th, it doesn't exist. Either we already know whether you came to class. Either you were there or you weren't there. So any event that already happened has no probability. Now I have to tell you that most events in life, we may think that they're impossible, but it's very rare that an event has a probability of 0. The probability of an elephant climbing up the building and walking into this room that I'm in, it seems like it would have a probability of 0, but you never know how things happen. So we would never say, it would be very rare that we would say that an event has a probability of 0. Okay? Okay. So let's just talk about outcomes, okay? Let's say that we roll a die. So what we can do, we talked about visual representations in statistics, and we saw that there are so many different visual representations. Recently in the newspaper, you've seen frequency polygons, you've seen histograms or bar graphs. In statistics, there are many of them, but in probability, there aren't that many. And one of the ways that we represent all of the different outcomes is using something called a tree diagram. We call it a tree diagram because it looks like a tree diagram. Some of you may have seen tree diagrams when you were younger. If you were creating family trees, those look very much like tree diagrams. So tree diagram is a visual representation of all the outcomes of an event. Okay. Each level of the tree diagram represents an event. So it represents all the outcomes in a single event. So when I say a tree diagram is a visual representation of all the outcomes of an event, I really should say more than one event. So let's put that in there. And it can either be the same event happening multiple times, or it could be different events, okay? So, for example, let's say that we have two things happening. Let's say that we toss a coin 2 times. And we want to know, well, what are all of the things that could happen when we toss a coin 2 times? So we already know this. We know that either we could get 2 heads, we could get a head first and then a tail first and then a head, or we can get we could get 2 tails. But we can represent this with the tree diagram, and a tree diagram can make it easier to, 1, list all the outcomes, and 2, make sure that we don't forget any of the outcomes. So this is what it looks like. The first level of the tree are the outcomes of the first event. This would be the first toss. Okay. So the possibilities for the first toss are either heads or tails. The second level of the tree would be the outcomes of the second toss. So we get a head first. Once we get the head, we can either get a heads or tails on the second toss. And if we get a tails on the first toss, we can either get a heads or tails on the second toss. Okay, so notice the outcomes for the second event are listed twice, okay? That's because we had 2 outcomes in the first level. So for each of the 2 outcomes in the first level, we're listing the outcomes that come in the second level, okay? The things that are listed in each level are the outcomes. The different levels are the events. So the first level represents the outcome of the first event. The second level represents the outcomes of the second event. And then each path of the tree represents an outcome if the 2 events occur together. So, for example, we have this first path, which is a head and a head. That gives us the first outcome. We could get 2 heads. Then we have a head and a tail. That gives us the second outcome. Then we could take another path. We could get a tail and a head. Then we can take the last path. The last path gives us a tail and a tail. This here is the sample space. Okay, each path gives us a separate outcome. And it's when the 2 events occur together. So if we only have 1 event happening, then you wouldn't do a tree diagram. Tree diagram requires multiple events. Let's take another example. This time, let's make it 2 different events. Let's say that here we toss a coin and roll a die. And I'll be specific and say 6-sided die. Okay, so we have 2 events here. The first event is going to represent the first level of the tree. So the outcomes for tossing a coin, we already know, are heads or tails. So that part of the tree diagram is the same. Okay. But this time, the second event, instead of having the outcomes of a heads or a tails, the outcomes are 1, 2, 3, 4, 5, 6. So from the head, we're going to have 1, 2, 3, 4, 5, 6. And from the tail, we're going to have 1, 2, 3, 4, 5, 6. This level represents the outcomes of the first event. And the second one represents the outcomes of the second event. Okay. Now here, our sample space, again, is each path. So we could get a heads and a 1. That's following this first path here. We go to the heads, and then we take that first branch, and we get a 1. Then we could get a heads and a 2. That's taking the heads branch and then going to the second branch over here that goes to the 2. A heads and a 3. A heads 4. Heads 5. And heads 6. We finished all of the branches that come out of heads. So now we go down here and we do the tails. So we have a tails 1. Tails 2. Tails 3. Tails 4, tails 5, and tails 6. That's our sample space. And notice that the number of outcomes in our sample space is equal to the number of branches in our last level. That's always going to be true. The number of branches in that last level. So in the first example, it was a total of 4. There were 2 branches for every one of the 2 here. So we have 2, 4. Here there are 6 branches for each of the 2 here. So we have 6 and then 12. So there are 12 outcomes in our sample space. Here there are 4 outcomes in our sample space. And here we just have 2 events. Let's do an example. Let's do an example with more than 2 events. So let's say that you are choosing an outfit. Okay. Now we're just going to ignore fashion for right now. We don't care if the outfit matches. We don't care about any of that. So here are the different possibilities. You have to choose a shirt, pants, socks, and shoes. Okay. So let's say that the shirts your sample space for the shirts is red or blue. Your sample space for the pants are black or tan. For the socks, you have solids, you have patterned, or you have polka dot. For the shoes, let's say that you have sneakers, and just let's leave it at that. You just have sneakers. Sometimes you can have an event with only one outcome. Okay? Okay, so let's do a tree diagram here. Now let's assume that you choose shirts, pants, socks, and shoes in that order, but it really doesn't matter. Okay? We don't care about the order in this case. So first event is going to be your shirts. So let's just label these. We'll call this event 1. This we'll call E2. We'll call this E3. And we'll call this E4. Okay. So the first level of our tree is going to consist of the outcomes for the shirts. So I'm going to abbreviate these just using the first letters, just so that our tree diagram will actually fit on the page. So we're going to start with red and blue. These are our shirts. Okay. Now from each shirt, we're then going to choose a pants. So from the red, we could either have black or tan. I'm going to put a blue here only so that you don't confuse it with the black of the pants. Okay. And so we could choose a red shirt and black pants, or a red shirt and tan pants. The same thing is true for blue. We can choose a blue shirt and black pants, or we could choose a blue shirt and tan pants. Then we have solid, patterned, or polka dot socks. So that's going to be in the third level of our tree. So there are going to be 3 branches that come out of each of these. We could have a red shirt, blue pants, and then either solid socks, patterned socks, or polka dot socks. So solid, patterned, or polka dot. I probably should have left a little bit more room here. Solid, patterned, or polka dot. Then for the blue, solid, patterned, or polka dot. For the tan, solid, patterned, or polka dot. So we could have red shirt, tan pants, solid socks. Blue shirt, black pants, solid socks. Each branch represents a different outcome for the 3 things together. Now we're going to add in that 4th event. And out of each of these, there's only one possibility, sneakers. So there's only one branch coming from each of these. That's okay. There's nothing wrong with just having one branch. And the total number of outcomes here, it's the total number of branches. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we won't write out the whole sample space. We'll just do some of it, and then I'll put a ... So red shirt, blue pants, solid socks, and sneakers. Red shirt, blue pants, patterned socks, and sneakers. Red shirt, blue pants, polka dot socks, and sneakers. We could instead have a blue shirt, tan pants, patterned socks, and sneakers. Okay, every branch gives us a different outcome of the 4 events together. Okay. So just a quick definition. If a sample space has only one outcome, it is considered a simple event. I should have written this earlier. So for example, rolling a 1 on a die is a simple event. In this case, choosing a red shirt, blue pants, and solid socks would be a simple event. That's because we only have one possibility. Right? Red shirt, blue pants, solid socks, and sneakers. That's it. That's your event. But just choosing a red shirt and blue pants is not a simple event. Because it has 3 outcomes. Those 3 outcomes are with solid socks, patterned socks, or polka dot socks. Okay. Okay. If we want to try and find out the number of outcomes in an event, we don't always have to draw a tree diagram, okay? We can use something called the fundamental counting principle. So I'm going to put this in a different color because it's really important. And we're actually going to use this a lot in probability. So the fundamental counting principle says if two events, I'll translate this. If two events occur in order, if the first occurs in m ways, and the second occurs in n ways, then the two events together occur in m times n ways. So here's what that's saying. Let's go back. We have two events happening here. The first event has two outcomes. The second event has two outcomes. If we want to find the total number of outcomes, we can take 2 times 2. The number of outcomes in the first event times the number of outcomes in the second event, and that's how many outcomes we have. That's because we have two groups of 2. When we toss a coin and roll a 6-sided die, there are 12 outcomes. That's because we have 2 groups of 6. This is the definition of multiplication. We have m groups of n. So the total number of outcomes is m, or 2, times n, or 6. This holds true if you have more than 2 events. So here, we can take and we can multiply all of them. We have 2 groups of 2. So 2 times 2 is 4. Now we have 4 groups of 3. 4 times 3 is 12. And we have 12 groups of 1. And 12 times 1 is 12. Okay? So total number of outcomes, you multiply the number of outcomes for multiple events occurring together. This is just another way of writing the fundamental counting principle. So again, let's go back and write down the way that we found the number of outcomes in each of these. So I'll put it in here. Number of outcomes equals 2 times 2, which is equal to 4. Here, the number of outcomes is equal to 2 times 6, or 12. Here, the number of outcomes is equal to 2 times 2 times 3 times 1, which is 12. If we have so if we're choosing a meal, from a menu with, let's say that they have 3 appetizers, 6 entrees, and we'll be optimistic and say 8 desserts. The total number of meals is 3 times 6 times 8. 3 times 6 is 18. 18 times 8 is 144. Okay, so we don't always have to draw the tree diagram, but if we were to picture the tree diagram, there would be 3 outcomes in the first level. From each of those 3, there would be 6 entrees. So in the second level, there would be a total of 18 branches. And then for each of those 18 branches, we would have 8 branches coming out of that. So that would be 18 groups of 8. So 18 groups of 8 gives us 144 branches. So in a case like this is where the fundamental counting principle becomes important, because maybe we don't care about what all of the different options are. We just care how many options exist. And in that case, we don't want to draw a tree diagram with 144 branches. That would be kind of insane. Okay, so this is how you would do it. Another example would be a safe with a 4-digit access code. Would have 10 times 10 times 10 times 10, or 10,000 possible combinations. So if you think about it, if you're trying to break into a safe and it's a 4-digit code, there are 10,000 possible combinations, which would take you a really long time. The same would be true If you think about your schedules and you think about the possible number of classes that you could choose, you would see that there's so many different possibilities, and all of that makes a big difference, okay? Okay, so let's talk about some, just some probabilities, okay? So first of all, we wrote this down before, but P of E is the probability of event E. Okay, it's the probability of event E, and we said it's the number of desired outcomes over the number of outcomes in the sample space, or total outcomes. So let's just take some examples, okay? Let's say we want to know the probability of rolling a 6 on a die. Well, there's only 1 6, and there are 6 possibilities, so it would be 1/6. The probability of getting heads when tossing a coin is 1/2. 2 possible outcomes, and there's only 1 heads. The probability of rolling an even number on a die, and when I say die, just assume it's 6-sided. It's 3/6, okay? 3 even numbers on a die. 2, 4, or 6. So there are 3 desired outcomes, and there are 6 outcomes in total. We could get a 1, 2, 3, 4, 5, 6, but what we're looking for is a 2, 4, or 6. Let's take another example. Let's say suppose we toss a coin and we choose a piece of colored paper from a bag with 1 green, 1 purple, and 1 black piece of paper. What is the probability of getting a tail and a green piece of paper, or a black piece of paper? Okay, so essentially what we're doing is we're saying, okay, well, what's the probability of getting a tail and a green And we're going to add that. Well, I don't want to make it this complicated. I'm going to change the way that we do this. So I'm going to underline in different colors what we're looking at because I don't want you to get confused. Notice I put this "or" in capital letters, okay? So that you can easily easily understand what we're looking for. We're looking for a tail and a green. So we're going to find the probability of that. And then we're going to find the probability of getting black. So it's two different events that we're looking at. Okay. So the probability of getting a tail and a green. Well, a tail and a green can only happen in one way. So we have one possibility there. But the probability of getting a black, this is 1 out of, and if we want to figure out the total number of outcomes, we're going to use the fundamental counting principle. There are 2 possibilities when we toss a coin, and 3 possibilities when we take something out of the bag, okay? So the 2 comes from the head or tail. And the 3 comes from the green, purple, or black. Okay, so fundamental counting principle. I'm going to put it in parentheses here, FCP. Fundamental counting principle says we take 2 and we multiply by 3. So the probability of getting a tail and a green is 1 out of 6. Now the probability of getting a black says we get a black piece of paper, but we could get a tail or we could get a head. It doesn't matter. So there are 2 possibilities here. We could get a head and a black or tail and a black. So this is tail and green. That's the only possibility. This is saying you could get a head and a black or you could get a tail and a black. That's where the 2 comes from. Okay, so this is 3 out of 6. It's the probability of getting a tail and green plus the probability of getting a black. So this could be a black and a head, or it could be a black and a tail. Okay, let's do another one. And for these, it could be helpful to create a tree diagram and then go along the paths. So let's actually do that here so that you can see clearly. So the tree diagram would give us a head and a tail, and then from the head we could have green, black, or purple. From the tail we could have green, black, or purple. So the probability of a tail and a green, there's only one path. For a black, there are 2 paths. There's the head in the black and there's the tail in the black. So there are 3 possible paths. Let's do another one. We'll do a few of these. The probability of getting a black or a purple and a head. Okay, so this is the same. What we're saying is we could get a black piece of paper and a head, or we could get a purple piece of paper and a head. So if we look at the tree diagram, black and head is one pathway. Purple and head is another pathway. So there are 2 out of 6 possibilities. The probability of getting a green and not a head Okay, now in this case, it's easy. If we don't get a head, then we have to get a tail. If there was a third outcome here, then we're just saying ignore all of these, because all of these give you a head. So we want to know what's the probability of getting a green and a tail. Well, there's only one. Now we want the probability of green or purple. So we're saying we don't care whether we get a heads or a tail. So the probability of getting a green plus the probability of getting a purple. Notice we're dividing this up. So the probability of getting a green, there are 2 possibilities, right? There's if we get a green and a head, or we get a green and a tail. So that's 2 out of 6. A green head and a green tail. Notice the order doesn't matter. Or another 2 out of 6, because we could get a purple in a head or a purple in a tail. So the number of desired outcomes is 4 out of 6. We could do the probability of not getting a head. So the probability of not getting a head is the same as the probability of getting a tail. And there are 3 possibilities. We could get a tail in a green, a tail in a black, or a tail in a purple. So this is 3 out of 6. Okay. So this is classical probability, and this is something that we're going to talk about more as we get into probability. I do want to mention that the probability of E prime is the probability of not E. Okay, E prime, this is 1 minus the probability of E. Okay, the probability of getting a tail is the complement of head. We call this the complement. So E prime is the complement of E, meaning it's the opposite of E. Probability of a tail is the complement of probability of the head. So we can just subtract from 1. If we're talking about getting a number that is not odd on a die, then we're talking about the probability of getting something that's even. So that would be what we mean by complements of events. And again, we'll do this more often. This is classical probability. Let's talk a little bit about empirical probability. So this is probability based on experiments. So in this case, the probability of an event would be the frequency of event E over the total frequency. This should be a Y. Okay, we've seen this before. This is the relative frequency. So we're just going back. Okay, I'm gonna try this again. I know that there was some sort of pause in the video. I know that we started with empirical probability somewhere. I'm not sure exactly where I left off, so I'm gonna start at the top. All of these notes were not here. They did just appear on your screen. That's because I've been having a ridiculous amount of technical difficulty. So hopefully in this video you did not hear me screaming at my computer at any point, because I have been for about the last 12 hours. So believe me, if you're having trouble, I understand how you feel. So usually I won't write out the notes like this, but because I have been having so much trouble doing the end of this video, I'm just gonna have it here. And hopefully you'll still be able to follow along, okay? So just to review, again, I apologize if I'm repeating myself. Empirical probability is probability that's based on experiments, okay? So it's different from classical probability, which is sometimes referred to as theoretical probability. Classical probability looks at chance and outcomes, possible outcomes. So let's take something simple like tossing a coin. If I were to toss a coin and say, well, what's the probability I'm gonna get head on the next toss? In classical probability, it's 1/2. Okay, that's because there's one desired outcome, a head, but there are two possible outcomes, a head or tail. Empirical probability is totally different. It's saying, okay, let me run an experiment. And in this experiment, I'm gonna toss a coin 100 times. And let me see how many times in that 100 times I get a head. So let's say I get 80 heads. Then the probability I'm going to get a head on my next toss is going to be 80%, or 80 out of 100, okay? If I toss the coin 300 times and I got 80 heads, okay, so same number of heads, but tossing it a different number of times, then the probability of my getting a head on the next toss would be 80 out of 300. If I did the experiment again, and this time I tossed it 100 times, but I only got 20 heads, then the probability of getting a head on the next toss is 20 out of 100, because I only tossed it 100 times. So the point here is that it's based on an experiment or on data that we already have, which means the empirical probability can change, and that's okay. So let's talk a little bit about how to actually calculate this empirical probability. So what we do is we take the frequency of the event, so that would be like the number of times that we got heads, and we divide by the total frequency. Now you've actually seen this before. You saw it at the when we started talking about visual representations and frequency distributions. We talked about the relative frequency. This is the relative frequency. That's what the empirical probability is. So let's take an example so that we can demonstrate how to calculate it. So suppose that we conduct an online survey and we're asking people what their favorite genre for books is. Genre meaning romance, science fiction, historical fiction, fantasy, non-fiction, which I didn't include in here, or criminal suspense. Okay, and we get the following results. So what we're going to do is we're putting this into a frequency distribution. Okay, so here are our classes: romance, sci-fi, historical fiction, nonfiction, fantasy, and criminal suspense. And then these are our frequencies. Of the people that we surveyed, 45 people said that they like romance, 80 people said that they like sci-fi, 25 said they like historical fiction, 40 said they like nonfiction, 100 said they like fantasy, and 120 said they like criminal suspense. So if we're calculating probabilities, the first thing that we need to do is find out the total frequency. So we can do that by adding together all of these frequencies. So 45 plus 80 plus 25 plus 40 plus 100 plus 120 is 410. 410 is the same as the total number of people surveyed. So total frequency is total number of people surveyed. So now let's calculate empirical probabilities. So what we're saying is, let's stop one more person on the street. So this will be the 411th person. And we're going to ask ourselves, what is the probability that this 411th person likes romance? So to figure that out, we're going to take the frequency of romance, which is 45, and we're going to divide by the total frequency. So 45 divided by 410 is 0.11. So that's the probability that the 411th person will like romance. Okay, and just to make that in terms that might be easier to understand, if we multiplied this by 100, we would get 11. So we would be saying there's an 11% chance that the next person will like romance. Let's say that instead we want to know what's the probability that the 411th person likes fantasy. So in this case, we're going to find the frequency of fantasy, which is 100. And we're going to divide by 410 again, because we asked 410 people. And we get 0.24 or 24%. There's a 24% chance that the next person is going to like fantasy. Okay, let's look at it from a slightly different perspective. Let's say that we want to know what's the probability that the next person doesn't like science fiction. Now, science fiction is one category here. So not liking science fiction would be somebody who likes everything other, okay? All of the other things. So what we can do this in one of two ways. We can either do everything else. So we could take the 45 from romance, the 25 from historical fiction, the 40 from nonfiction, the 100 from fantasy, and the 120 from criminal suspense. And we can add all of that together because that's everything but science fiction. And we get 330. We divide by 410, and it's 0.80. So there's an 80% chance that the next person we ask is going to say something other than science fiction. Okay, but this can be a little bit difficult to calculate because right now we have 6 categories. It's not that difficult to take the 45 plus 25 plus 40 plus 100 plus 120. But if we had 100 categories, then we would be adding 99 numbers together, all but one category. And that could be very time consuming. So it can be more efficient to find the probability of the complement. So we talked about the complement. The complement is the opposite. Okay, so if we're saying the probability that somebody doesn't like science fiction, we're really asking, what is the probability that somebody does like science fiction? And then we're going to subtract that from the total. And in probability, the total is always 1. It's a definite thing. Definite thing happening is 1. So if we want to do that, the probability that somebody likes science fiction is 80 out of 410. So 80 out of 410, we calculate that first. That's 0.20. And we're going to subtract that from 1. So 1 minus 0.20 is 0.80. Notice it's the same. Okay? So this is like an equivalent example is if we had 100 people in a room and we wanted to figure out how many girls there were. Okay? Now, we could either count the number of girls or we could count the number of boys and subtract that from the 100 people in the room because that's going to tell us how many girls we have. And it's just going to depend on what's more efficient. If we only have 5 girls in the room, then it makes sense to count the number of girls. But if out of the 100 we had 90 girls, it's going to be a lot easier to count the number of boys and subtract that from 100, and that'll give us the number of girls. So it's just a matter of perspective. What's easier? And sometimes finding the probability of the opposite and subtracting from 1 is easier. Okay, let's take another example of empirical probability. So let's say that we were taking social networking users and we were classifying them by age. So we have ages 18 to 22, 23 to 35, 36 to 49, 50 to 64, and 65 plus, okay? There were 156 people, social networking users, that fell into the age group 18 to 22. 312 who were 23 to 35 years old, 254 who were between 36 and 49, 195 who were between 50 and 64, and then 58 who were 65 or older, okay? The total frequency is just the sum of the frequencies. So we do 156 plus 312 plus 254 plus 195 plus 58, and we get 975 people. Okay. So we want to know, if we take the next social networking user, what is the probability that they are between 18 and 22? So we go to the 18 to 22 category, and there are 156 people in that category. So we do 156 over the total, which is 975. And if we put that into our calculator, we get 0.16. So that means that if we look at the next social networking user, there is a 16% chance that that user is between 18 and 22, okay? If instead we wanted to know what is the probability that the next person is between 23 and 35, so this is the same thing, I just wrote it out here, okay, just to make it clear what we mean by probability of 18 to 22, or probability of 23 to 35. So here, we go to the 23 to 35 category instead, and we get 312. So we take 312 and we put it over the total. And in this case, we get 0.32. So there's a 32% chance that the next person that we choose, the next social networking user, is between the ages of 23 and 35. Okay. Let's do another complement. So let's say the probability of our next person not being over 65. Okay, so not being over 65 would include all of these other categories. All of these other categories are under 65 years of age. So we could calculate it that way. We could do 156 plus 312 plus 254 plus 195. That gives us 917. And then we divide by the total. 917 over 975 is 0.94. So there's a 94% chance that the next social networking user is under 65 or not 65 plus, okay? Now again, there are only 5 categories here, so this wasn't such a big deal. But let's do it the other way. Let's use the complement instead. Let's find the probability that somebody is 65 plus, okay? So if they're 65 plus, then that means that there are 58 people who are 65 plus. 58 over 976 over 975 is 0.06. But then we have to subtract that from 1, and we have to subtract that from 1 because we want the opposite, okay? So 1 minus 58 over 975, or 1 minus 0.06, is 0.94. Notice we get the same number. That's because we're calculating the same thing, just from a different perspective. We're counting the number of people 65 plus and subtracting that from a total probability. So notice we're not subtracting from the total frequency because we're taking the probability of 58 over 975, and total probability is 1. So if we're using probabilities of complements, then we always subtract from 1 because 1 is equal to the total probability. Okay, and this is empirical probability. So I'm going to just emphasize one more time that empirical probability could change, because if we chose 975 different people, these frequencies might be different. So the probability of 18 to 22 might not be 0.16 anymore. That is okay. It is okay for empirical probabilities to change because they are based on experiments. Okay? It is one of the reasons why we use theoretical probability more, or classical probability. Okay? And again, what we're doing is we're taking data that we already have and we're using that to predict the future. Okay? And that's it for this video. We're going to go more in depth in probability in the next video.